is lowering the temperature to increase heat equity. One of the things that we have talked about today is the fact that the world is warming. So what I'm sharing with you today, first of all, is a recently published study lowering the temperature to increase heat equity, which is published in Atmosphere late last year. This builds on the microscale study I did and was published in 2021 in IJ Biomet, which were my PhD field results, microscale field results. So why are we here? I won't belabor the point exhaustively, but anthropogenic change is driving massive changes in urban climate regimes. We are seeing anthropogenic change has changed the natural world to a point that it is no longer recognizable, and it's come to the point where we live is no longer livable because heat is modifying our physiological reactions, our biological reactions, and our social reactions. I don't need to belabor the point of this is driving climate change, but perhaps one of the most important things I want to talk about is all of this is, aside from the fact that we have a changing climate that's occurring and we have mass disasters that are occurring, we also have this interaction with the built form, which is exacerbating all of this change, and one could arguably say driving. So what does that mean? Well, we need sustainable approaches to urban development, to new urban development, but to retrofitting development in order to increase resilience, to improve our climate, but also to improve our public health outcomes. So the focus of this study, as I said, it's building on my microscale results. The reason I chose to do this study is I wanted to see, could we replicate microscale results at the mesoscale? So we know, well, we'll get to this, but we know that change, good, positive, beneficial impacts from green infrastructure are possible at the site level, at the building level. Could we see something translated equally at the city level? So the purpose of the study is to evaluate the effect of nature-based solutions, specifically green infrastructure, and this is my typology for green infrastructure, on near surface air temperature and land surface temperature in Toronto, Ontario, which is the largest city in Canada. A little bit about the methodology. So we used, for the microscale sensing, HOBOs, which are temperature loggers. These were simultaneous monitoring across all sites, as well as remote sensing, and we use Landsat 8 remote sensing specifically. While there are temporal limitations, it is ideal because it's quite granular and you get a fair bit of detail. And what this did for the second measurement, remote sensing campaign, is it allowed for a correlation between land surface temperature and NDVI, which is a big mouthful, normalized difference vegetation index, to urban form and the changes on land surface types. With respect to the first measurement campaign, this was undertaken over a series of different applications, different types, different building types, different neighborhoods, and different applications of green infrastructure. Okay. In terms of the study area, so right here, these are the four microscale sites. The first is the Mountain Equipment Co-op building in downtown Toronto. It's sort of southwest within the city. It's an extensive green roof, 10,000 square foot green roof. At one time, it was the largest green roof in North America. It's the first green roof I ever stepped on when I was doing my master's degree, and is why I fell in love with green infrastructure. Unfortunately, this building is no more. It has been torn down and turned into condos. So this is kind of its swan song. The second site is Carrot Common. It's located sort of centered toward the east of the city. It's a little further inland. It has four different applications of green infrastructure: a semi-intensive growing roof, an extensive green roof, a green wall, and a rooftop medicine garden. And then the remaining two sites here are on the University of Toronto Scarborough campus. There are two buildings, the Instructional Center and the Environmental Science and Chemistry building, which contain a rooftop garden and an extensive green roof. Now, in terms of the mesoscale study, we looked at the proper boundaries of the City of Toronto It's a population of approximately 3 million people. If we take in the surrounding Greater Toronto area, we're looking at approximately 6 million people. The city of Toronto is very highly urbanized. You've got different types of urban form, but it is also touted as being the city in the park because there is quite a bit of natural greenery dispersed all throughout the city. So, in terms of the microscale results, and I'm just going to go through these very quickly. Greener systems, this is the very beautiful, once upon a time, Mountain Equipment Co-op green roof. I have thermal imaging here. It's only meant to be anecdotal, but it's just to show you what a huge difference, a visual difference you can see in systems. The next, this is the greener system on the University of Toronto building. This is the rooftop garden in the instructional center. And this is the Carrot Common Green Roof Medicine Garden and Green Wall area. This is the forestry systems, urban forestry and vegetation systems on the University of Toronto campus. This is vertical systems here in the Carrot Common area. And just to give you the microscale results for each of the sites, we saw the biggest reductions here in urban agricultural systems. So the growing roof, the medicine garden, and the rooftop garden. However, across all different types of green infrastructure, we do see reductions of approximately, I'm going to say about half a degree across all systems. So regardless of location, geography, building type, where it was located in the city, we see reductions through the application of green infrastructure. If we go to the mesoscale results, what we see here, and I want to draw your attention to this because the very last, or the third last slide, I want you to look for this dough map pattern that you're going to see with each of these maps. So the top map, figure A, is land surface temperature, bottom is in dBi. And what we see is the values, the LST values range between 20 and 38 degrees Celsius, except where there are water bodies. So water bodies right here, this is Lake Ontario, it's a massive part of the chain of Great Lakes. Except for those water bodies, we see values as low as 19.5 degrees. But where you see ravines, natural areas, those were the coolest, with that value between 22 and 25 degrees. Now the natural areas within the city, so the natural types of what I'm calling here green infrastructure, are forested areas, ravines, meadows, wetlands, urban parks, and various successional lands or county forests. The urban green spaces really stood out due to their cooling effect, and we see values varying between 25 and 28 degrees. Where we saw flat grass, so homogeneous grass areas, they had higher LST values than compared to forested areas. Public parks were recorded LST values of up to 5 to 10 degrees lower than built-up surroundings. The highest values we saw were recorded for the compact built-up areas of the city, so really industrial areas. And these have the highest land surface temperature, reaching above approximately 35 degrees Celsius. Built-up areas with less vegetation had very high LST values. Where you have highly urbanized areas with tree-lined streets or yards with a lot of shrubbery and greenery, they had reduced LST values. We also note that there was an additional cooling effect that's associated to the proximity of the lake down here. Here, this is another map. So this is the mean LST and dBi. And very similar, trees and dense vegetation predominate in decreasing that land surface temperature. Again, flat grass surfaces have a reduced cooling effect. Industrial areas are 15 degrees Celsius higher in temperature. Urban areas that have more vegetation have lower LST values. And this is consistent with other studies, specifically Renner and Hussein. They did some work back in 2008, and they recorded almost similar values, temperature values, and even in the green areas. So we know that this is not an anomaly. So the point of this entire presentation. These are not my maps. These are maps that were produced. This is by the City of Toronto Public Health Department, and this was by Toronto Revenue. So what are we seeing here? And remember I told you about that donut pattern on the two maps. So if we just go back for 1 sec, I want you to look right here, LST mean and DBI. In the top map, what we are seeing here is a heat vulnerability map which identifies building stock in the city of Toronto. And these are the tallest, oldest buildings built in the 60s and the 70s. What we see down here is basically a wealth map. And the richest areas are here in green. And the poorer areas are in the lighter colors. And they almost completely correspond. So what we're seeing here is that areas that are wealthier have a lower vulnerability to heat. So in conclusion, what do we see with our microscale data? Well, the data collected is consistent with the hypothesis that multiple types of green infrastructure can reduce near surface air temperature, regardless of location, geography, or land use type. It's novel because in this particular study, multiple types of green infrastructure were tested simultaneously across different treatments. It was a controlled field experiment. Perhaps what really stands out is that productive, so as in food producing applications, have temperature regulation benefits that really haven't been previously evaluated in other studies. So urban agriculture systems, while they can reduce near surface air temperature in urban and suburban settings, they have the additional co-benefit of enhanced food security. This is significant within urban areas, especially where you have areas of vulnerable populations. At the mesoscale, we see that there is a link between urban form and land surface temperature. I don't think it's a surprise to anybody here. Industrial areas have higher LST values than forested areas. Urban areas with more vegetation have significantly lower land surface temperature values compared to built-up areas. And what this shows us in Toronto is that urban vegetation and forestry systems can significantly lower heat load. Where does this take us? Well, wide adoption of multiple different types, and I think we've learned that today. Multiple types of green infrastructure can be meaningful in mitigating rising temperatures in urbanized settings. And maybe more specifically, what we can see, if we look at the series of maps I just showed you, from what we see with the satellite remote sensing to the actual public health and wealth maps, we have a methodology with how we can prioritize where we put green infrastructure, where we plant trees, where we put green roofs and green walls to actually reduce health risks from extreme heat and to improve heat equity across communities. And I think that these results in this methodology can be easily replicated across communities in both local north and south. So thank you. And I have to make one last plug. So give me 1 second. If any of you want to collaborate or you have any interest in exploring these themes further, I would ask you to contribute or ask me. I'm guest editing this special issue, so if you are interested, it's an opportunity maybe to explore this further. So thank you for your time.
Okay, one or more questions for the Vidya.
I can't compete with coffee, so my feelings aren't hurt.
There is no question for that. Okay, thank you, Vidya, so much.